Take a look at the base physical blueprints for Earth and Venus. They are nearly identical. Venus is a rocky terrestrial planet with 81% of Earth's mass and 95% of Earth's radius. Based on size and composition alone, they are planetary twins. But the reality of modern Venus is incredibly hostile. The average surface temperature is 464 degrees Celsius, hot enough to melt lead. The sky is filled with clouds of sulfuric acid, and the atmospheric pressure pressing down on that crushing rocky surface is 92 times heavier than what we experience at sea level. Venus's orbital mechanics are just as strange. It spins backward compared to most of the solar system, and it rotates so slowly that completing a single turn on its axis takes 243 Earth days. Since its orbit around the Sun only takes 225 days, a single day on Venus is technically longer than a Venusian year. Two rocky bodies formed in the exact same solar neighborhood, out of the exact same starter materials. Yet one evolved into an ocean-covered oasis, and the other devolved into a toxic wasteland. Figuring out where Venus took a wrong turn provides the exact data we need to map the precise, fragile parameters that keep our own planet habitable. If we wind the clock back a few billion years, Venus was sitting comfortably within the solar system's habitable zone. It possessed vast oceans of liquid water on its surface and a mobile crust with active continental geology. The catalyst for its destruction came from the Sun. Over hundreds of millions of years, the young Sun matured. Its core contracted, causing its luminosity and heat output to steadily rise, bathing Venus in increasingly intense solar radiation. This chart illustrates the planetary feedback loop that followed. Rising surface temperatures caused the oceans to evaporate. That water vapor filled the atmosphere, acting as a powerful greenhouse gas. It trapped incoming solar heat, which then caused even more surface evaporation. The cycle fed continuously on itself. The heat drove more evaporation, the vapor trapped more heat, and the temperatures climbed until every drop of liquid surface water boiled away. Losing the oceans dictated everything that happened next. Water on a rocky planet is a critical component of its internal mechanics, and its total evaporation destroyed the planet's geological future. On Earth, water lubricates the crust and allows tectonic plates to slide and subduct. On a bone-dry Venus, the crust locked tightly into a single stagnant shell. Without active subduction zones to drag carbon down into the mantle, carbon began permanently trapping itself in the atmosphere. Deep underground, the mantle was still generating intense heat. With the tectonic vents sealed shut, that pressure built up continuously until the crust fractured. This triggered catastrophic, continent-spanning volcanic floods that pumped massive volumes of carbon dioxide straight into the sky. Eventually, the planetary engine stalled entirely. Without a mobile crust to release internal heat, the convection current circulating inside the molten core slowed down and stopped. Because a churning core generates a planet's magnetic shield, Venus's magnetic field simply collapsed. The upper atmosphere was now fully exposed to the solar wind. Charged particles from the Sun bombarded the planet, tearing apart the evaporated water molecules and sweeping those lightweight hydrogen atoms out into deep space. The result is an extreme atmospheric state. Near the surface, the heat and pressure are so immense that carbon dioxide becomes a supercritical fluid, a bizarre state of matter that behaves like a dense liquid and a heavy gas at the exact same time. The evaporation of the oceans triggered a direct geological domino effect. The water vanished, the crust seized up, the core stagnated, and the atmosphere compounded into a toxic, crushing blanket. But if microbial life evolved in those ancient Venusian oceans before they boiled away, it might have adapted. As the surface grew too hostile, microbes could have migrated upward. This graph plots the planet's altitude against temperature and pressure. It reveals a specific layer 50 kilometers up, where conditions remarkably match the surface of Earth. Here, the atmospheric pressure drops to a normal level, and temperatures sit comfortably between 30 and 80 degrees Celsius. In 2020, astronomers pointed the James Clerk Maxwell telescope at this exact cloud layer and detected trace signatures of phosphine gas. On rocky planets, phosphine is almost entirely produced by anaerobic microbes in oxygen-starved environments. Follow-up observations using the Green Bank telescope revealed preliminary signs of ammonia. Ammonia is another strong biosignature gas that is typically produced by nitrogen-converting bacteria or industrial processes on Earth. These chemical anomalies forced shift in how we view the planet. Beneath its status as a dead, ruined world, it may serve as an active laboratory for extreme biological survival. After decades of sending rovers and orbiters almost exclusively to Mars, space agencies and private aerospace companies are launching a new fleet of forensic probes to Venus. NASA's Veritas orbiter will use high-resolution radar to pierce the opaque clouds of sulfuric acid. By mapping the surface topography, scientists will scan for the physical remnants of ancient continents and check for active, ongoing volcanism. Missions like Da Vinci and the privately funded Venus Life Finder will take a direct atmospheric approach. They will drop physical probes straight down through the cloud layers to hunt for complex organics and chemical proof of life as they fall. Returning to Venus is ultimately about looking into a planetary mirror. By analyzing the mechanics of our solar system's worst climate disaster, we extract the exact data needed to preserve the lucky, delicate balance of Earth.